Now, let's talk about limitations of the urine osmolar gap. Urease-producing bacteria disrupt urine osmolar gap, and this leads to ammonium mismatch. In the urinary bladder, bacteria like Proteus and Klebsiella produce urease that break down urea into ammonia and carbon dioxide. Ammonia is produced in the bladder, not in the kidneys. This ammonia is not the same as renal ammonium excretion in response to acidemia. In acidic urine, ammonia grabs protons in the bladder and forms ammonium, but this happens post-kidney, so it does not represent renal acid excretion. This ammonium produced in the urinary bladder, not in the kidneys, appears in the collected urine specimen. However, ammonium raises the measured urine osmolality, falsely suggesting high ammonium excretion. The result? Urine osmolar gap falsely elevated even though kidney ammonium excretion is not high. Non-ammonium solutes, for example alcohols and mannitol, falsely raise urine osmolar gap. These are osmotically active but not accounted for in the calculated osmolality. The result? Urine osmolar gap is falsely high, potentially mimicking increased ammonium excretion even when renal ammonium excretion is not elevated. Incomplete dissociation of sodium and potassium in very concentrated urine leads to an underestimation of calculated osmolality. But how does this happen? Let's review. The urine osmolar gap is measured urine osmolality minus calculated urine osmolality. Measured osmolality from an osmometer is correct. It measures total particle effect, including unmeasured ones like ammonium. Calculated urine osmolality equals 2 times the sum of urine sodium and potassium plus urine urea nitrogen divided by 2.8 plus urine glucose divided by 18. The multiplication by 2 for both sodium and potassium in this formula assumes that all these cations are fully dissociated and balanced by anions, primarily chloride, in the urine. In dilute or normal urine, we assume that each sodium, potassium, chloride, ammonium, and other ions are fully dissociated and each acts as a separate particle. An example of this is sodium chloride dissociates into sodium plus chloride, 2 particles. Ammonium chloride similarly dissociates into ammonium and chloride, 2 particles. The calculated osmolality matches measured osmolality reasonably well. Each ion counts as a separate particle and particles determine osmolality. But in very concentrated urine, something different happens. In highly concentrated urine, due to dehydration, high ADH, etc., ionic strength becomes very high. Ions are packed closely together. Opposite charges attract and form temporary ion pairs. Sodium plus chloride forms sodium chloride, ion pair, and this behaves as one particle. Similarly, ammonium plus chloride forms ammonium chloride, ion pair. These pairs reduce the effective number of free particles in solution. Fewer free particles leads to lower measured osmolality compared to what you'd expect because the number of free ions in the solution are the primary contributors to osmolality. Measured osmolality from an osmometer is correct. It measures total particle effect, including unmeasured ones like ammonium. But the calculated urine osmolality from sodium, potassium, urea, and glucose is overestimated because we assume all ions are fully free. If calculated osmolality is too high because of wrong assumptions about free ions, then this leads to urine osmolar gap becoming falsely low. Thus, you underestimate how much unmeasured osmoles, like ammonium, are really there.